Usually we can easily identify objects in images where only line drawing is given. Lines correspond to edges or sudden changes in images. Intuitively, most semantic and shape information from image can be encoded in the edges. It is more compact representation than original images, so it can be very useful to extract edges from image to use it for the recognition. The ideal result is the drawing of an artist, but artist uses object-level knowledge, and in image processing we rarely can use object-level knowledge. Now we will consider only basic algorithm without machine learning, but I will mention how the machine learning algorithm can be constructed for edge detection. We will consider edges as points of rapid change in the image intensity. Such points can be identified by considering first derivative of image intensity. Edges will correspond to local extrema of derivative. On the slide, I'll give a one-dimensional example from one row in image. Because image is a two-dimensional function, we need to calculate image gradients as a vector of partial derivative of image intensity function. So image gradient is a vector where first element is partial derivative of f by x and second element is partial derivative of f by y. The gradient direction is given by arctan of partial derivative of f by y over partial derivative of f by x. The edge strength is given by the gradient magnitude. Because images are discrete, we could approximate partial derivative of optical image with finite difference in discrete images. Finite difference can be easily written as a simple convolution, for example with 2x1 filter kernel and values -1 and +1. Other approximation of derivative filters exist. I put here Roberts operator, Prewitt, Sobel and Shar operators. These operators both smoothes and estimate finite differences in images. They produce visually similar results. Here the example of edge maps computed by convolution with these filters. You can see the difference between filters is mostly small. Consider a single row or column of the real image. Usually the image contains noise. We plot intensity as function of position. Finite difference filters respond strongly to noise. Noise results in pixels that look very different from their neighborhoods. So finite difference will produce a lot of false responses. Generally, the larger the noise, the stronger the response and the larger the number of strong responses. So if image contains noise, then the real edge can disappear, like it's demonstrated in this slide. The solution is to apply Gaussian smoothing first to reduce the noise. After smoothing, edge detection kernel can identify the edge in our image. Because convolution is associative operation, we can combine both smoothing and differentiation kernels into one filter kernel. This saves us one operation and produces the same result as applying smoothing and differentiation operator successively. Here are visualizations for derivative of Gaussian filter, which can be used for gradient estimation in real images. I give visualization of two filters. One estimate gradients in x direction and one estimate gradient in y direction. Smooth derivative removes noise, but blurs edges in images. The larger the Gaussian filter, the stronger the smoothing. As a result, we find images in different scales when applying smoothing with different filter kernels. In this example, if we use small filter, we get a lot of small edges, small details. When using larger filter, we detect gradients only corresponding to large objects in the image. Gradient magnitude estimation is not a complete edge detector. Edges are usually thick stripes or ridges of large image gradients, as you can see in this example. Also, we receive only a disjoint set of points with large gradients, without connectivity information that link neighboring points into real edges. These problems were addressed by well-known Canny edge detector. This is probably the most often used edge detection algorithm, despite the fact that it was proposed in 1986. It adds two steps for gradient estimation. First is non-maximal suppression. During this step, we thin multi-pixel white ridges down to single pixel width. Second is linking edge pixels together to form continuous boundaries. Here an example. We take an original image of Lena and apply gradient estimation first. We obtain map of gradient norm. You can notice a lot of thick ridges at the edges. Now we apply non-maximal suppression. This can be done in several ways. The easiest is just to leave the pixels that are local maxima in the square neighborhood, example for 3 by 3 pixels. The more complicated way is to identify the points in neighboring pixel rows along the image gradient vector. At Q, we have a maximum if its value is larger than those of both P and R. To get values in P and R, we should interpolate from neighboring pixels to get these values. So we found a local maximum along the image gradient vector. Edge linking is performed as following. Assume the marked point is an edge point. Then we construct the tangent to the edge curve, which is normal to the gradient and this point, and use it to predict the next point. This light is either R or S points. We select the point with largest gradient and link it to the current point Q. When linking edge points, we use hysteresis. Hysteresis is just two thresholds. We use high threshold to start edge curves and low threshold to continue them. This allows us to trace weak edges if they are connected to the strong edges. Weak edges themselves won't be detected with hysteresis thresholding. Here is an example of thinning or non-maximal suppression applied to the edge map obtained for this particular image. Hysteresis allows us to achieve a balance between the amount of detected edges and noise. If only one threshold is used, we either miss weak edges, which are extensions of strong edges, or get a lot of noise from weak edges alone. By varying the sigma in gradient computation, or the size of Gaussian smoothing, or the size of derivative of Gaussian filter, we can detect edges on different scales. Large sigma detects large-scale edges. Small sigma detects fine features in images. On this example, you can see that by increasing the size of sigma from 1 to 2 removes vertical lines originated from stripes on the wall. The change in image intensity is not the only source of edges in real images. As can be seen from the slide, change in color or texture also gives us visible edges in images. But such changes cannot be detected by image gradient or Canny operator. Of course, there are more advanced methods which can achieve this result. Mostly they consider edge detection as pixel classification problem and use machine learning techniques. We create a dataset of ground truth labeling of edges and train image classifier that classify pixels to either edges or non-edges by considering different features like texture, color, image intensity. But for many computer vision tasks, Canny edge detector proves to be sufficient. For example, it's often used as feature extractor and produce features which are later used for image recognition.